Hello everyone and welcome to your 511-1 practice exam question. Today's topic is bond theory, symmetry, and hybridization. So to start off, let's have some review. First of all, a reminder about the conventions for naming symmetry of bonds. If a bond is symmetric about the bond axis, it is called a sigma bond, and bonds that are not symmetric about that axis but have symmetry above and below the axis are referred to as pi bonds. Now, since sigma bonds are typically our single bonds or our first bonds in the case of multiple bonds, we want them to reflect the geometry, which means they can be made either from s orbitals or from hybrid orbitals, which depend on the geometry. The first of these are sp hybrid orbitals, which are made from an s orbital and a single p orbital. As they have two orbitals in, will have two orbitals out, and thus they have two lobes and are suitable for atoms with a steric number of 2. This leaves the lobes at a 180-degree angle, and two leftover p orbitals which are capable of making multiple bonds. Similarly, sp2 hybridized orbitals are made from an s orbital and two p orbitals. 3 orbitals in equals 3 orbitals out, so 3 lobes suitable for a steric number of 3, leaving 1 p orbital left over to make multiple bonds, and the lobes at a geometrically appropriate 120-degree angle. Finally, sp3 hybridized orbitals toss all of the available atomic orbitals into the mix, so the s orbital and all 3 p orbitals. This means that seen on atoms with a steric number of 4 has no p orbitals left over, so no capability of making multiple bonds, and the lobes are at an 109.5-degree angle. Also, a quick reminder about polarity, since it's mentioned in this problem. Covalent bonds that have a difference in electronegativity between the two atoms will be polar, with the more electronegative atom having a larger share of the electron density. The degree to which a bond is polar depends on the difference in electronegativities between the two atoms. Now on to the problem. We are presented with a molecule that is interesting, possibly because it's an insecticide, or more likely in our case because we're being tested on it. 5 bonds are pointed out to us, and our job is to say the basically interesting things about these bonds. So, which orbitals are overlapping to cause them, what their symmetry is, etc. Starting with bond 1, we see that we have a single bond, which limits us right away to sigma bonds, which are made from hybrid orbitals and s orbitals. When we account for the lone pairs on the oxygen, which aren't shown in this drawing, both the oxygen and the carbon have a steric number of 4, and thus are sp3 hybridized. So the sigma bond is made from those hybrid orbitals, which is the 2sp3 on the carbon and the 2sp3 on the oxygen. Now we move on to bond 2, which is also a single bond, so we're dealing with a sigma bond made from hybrid orbitals and/or s orbitals. Chlorine is a terminal atom, so we don't need to hybridize it, we can just use its s orbital. And carbon we do need to hybridize. It has a steric number of 3, and thus is sp2 hybrid. So we have a sigma bond between carbon's 2sp2 orbital and chlorine's 3s. Moving on, we have another single bond, so another sigma bond, this time between a carbon and a nitrogen. Both of them have a steric number of 3, so both of them are sp2 hybridized, and so the sigma bond is made from carbon to sp2 and nitrogen to sp2. When we get to bond 4, we're finally dealing with multiple bonds, which consist of first a sigma bond and then pi bonds. So this is a double bond. It will have one sigma bond between hybrid orbitals and one pi bond between the leftover p orbitals. The nitrogen and the carbon are both sp2 hybridized here because they both have a steric number of 3. So we have a sigma bond between carbon 2sp2 and nitrogen 2sp2. We also have a pi bond between the leftover p orbitals, which we denote as pz. Finally, we have bond 5, which is also a double bond, so 1 sigma bond and 1 pi bond. The nitrogen has a steric number of 3, so it's an sp2 hybridized, and there's no need to hybridize the oxygen as it's a terminal atom. So we take our sigma bond from the hybrid orbital, which is nitrogen 2sp2, and the s orbital, which is the oxygen 2s, and we take our pi bond from the pz orbitals on each of them. For the next part of the problem, we're asked for the geometry around each of the nitrogen atoms, remembering that each of these nitrogens can be assumed to have an octet, and that we should add in lone pairs as necessary. Nitrogen A and nitrogen B all have 3 bonds around them and require an additional lone pair for an octet. This makes them sp3 hybridized, and the geometry is trigonal pyramidal. Nitrogen C and nitrogen D both have 2 bonds in a lone pair, which makes it sp2 hybridized and bent. Nitrogen E has 3 bonds around it and no lone pairs, so it is sp2 hybridized and trigonal planar. Finally, we're given a small question that asks, not including the bonds with nitrogen E, which bond in the molecule would you expect to be most polar? So if we don't include any of the bonds with nitrogen E, we're left all with bonds that are carbon and something else. So we want to choose the other thing that has the greatest electronegativity difference with carbon, and that's the oxygen. So either of the carbon-oxygen bonds, which are basically equivalent, would be what we expected. Note that if you said carbon and chlorine, you're somewhat on the right track. However, it turns out that as per periodic trends, oxygen and carbon have a greater electronegativity difference than do carbon and chlorine. And that does it for this practice test question. Please watch the rest of the questions, and good luck on the test.